Today we'll be discussing the perfect gas equation. The perfect gas equation is PV is equal to nRT. First question is, how do you arrive to this equation? This equation is a set of empirical facts, or empirical laws. Empirical basically meaning it came from observations. First observation was Boyle's one, which we call Boyle's law. And he found pressure is inversely proportional to volume. And if we multiply this by K, we can say pressure is equal to K over V. And therefore, pressure is equal to pressure times volume is equal to K. Basically, a pressure that has a fixed volume is constant. That was Boyle's law. The next law was Charles' law. Charles' law states pressure is proportional to temperature under certain conditions. Volume is proportional to temperature under certain conditions. In both cases, you can see how it works. If I decrease the volume, I increase the pressure. The example is a balloon. If I squeeze the balloon to make a smaller volume, the pressure inside increases. Same thing here in Charles' law. If I was to reduce the temperature of the balloon, let's say with liquid nitrogen, the pressure inside would drop and the balloon will shrink. And also the volume also does change as well under these certain conditions. Another law is Avogadro's law, and he found that volume is proportional to the number of moles. This basically means the more molecules you have, the more space they'll take. Okay, so now how do we get to this ideal gas equation? Well, we use Boyle's law, PV is equal to K, and recognize PV is always equal to PV no matter what circumstance. This is always the case, it's a mathematical fact. Two things that are identical are equal. Okay, so how do I get this? So to get PV, I multiply this one by this formula, and we get P times V, so times is equal to, well, not equal, proportional to NT. So PV proportional to NT. If I multiply by a constant, let's say call it R, this will become equal. PV is equal to nRT. And this is our perfect gas equation. Equation of state of a perfect gas. Okay. Things we should quickly discuss are iso, the word iso. Iso basically means single. We can have isocores, isotherms, and isobars. This is single, all of these are single volumes, single pressures, the temperature, and single pressure. Where does this come in use? When we're trying to see the relationship. For example, for Boyle's law, if you had pressure against volume, let's say I start off at a large volume, therefore the pressure is going to be small. So in a large volume, pressure is going to be small, so somewhere here. If I start to reduce the volume of my container, such as the balloon, the pressure starts to increase faster and faster, and until you get to such a small size, the pressure increases dramatically. And this is the content of Boyle's law. And this happens, what this line here is happening at, is an isotherm. Because we did this entire experiment of decreasing the volume of the balloon at a single temperature, let's say 20 degrees Celsius. If I was to do it at 30 degrees Celsius, the lines will look like that. Or if I did a higher temperature, it would look like this. Let's say 30, and let's put it at 40. Basically, all it's saying as the temperature increases, the pressure is also going to increase. As you can see through the graph, there's greater pressures. All right. Okay, next thing. Now, the perfect gas law is a case of limiting law, which basically means it's true for up to a certain extent. When is it true? When the pressure is tending towards zero. So when you have zero pressure, this equation becomes very true. But it's usually fairly accurate enough to do for experiments. at pressures that are roughly equal to 1 bar, and pressures that are roughly equal to 1 bar and reasonably high temperatures. This formula usually works. Okay, that's everything referring to the perfect gas equation I can think of. Last thing would be, partial pressures. It's sometimes reasonable or easy to talk about the pressure that each individual gas makes inside of a container. So if I had a container of air, it's made of a mixture of molecules. So oxygen, you've got nitrogen, you've got other molecules like carbon dioxide. So if I want to know the individual pressures, I'll define the, mole fraction. The mole fraction is basically, if I had a element X or molecule X divided by the total number of moles. So the number of moles of this, X molecules, divided by XT, the total number of moles, is equal to mole fraction. So basically, it's the amount of moles confined by the total moles of all of the mixture of gases. So the amount of moles we're looking at, so example, let's say carbon dioxide, divided by the total number of moles of everything. That's mole fractions. Mole fraction, and then there's partial pressures. Partial pressure is equal to the total pressure. The word total is very important here. Multiplied by the mole fraction, or the probability or chance of having that many molecules. Mole fraction. That's the partial pressure. Now Dalton had a law, I believe. I don't know if it's a law statement. Well, Dalton said that if you removed all the gases in a container, so let's say we had a container of oxygen, nitrogen, I'll call them as blue, and carbon dioxide, I'll draw a line through them. If I removed all the containers, all the molecules, except for one I'm interested in, let's say I'm interested only in oxygen, then the pressure of the oxygen molecules will be equal of oxygen molecules in a mixture is equal to pressure if it was alone. Pressure if it occupied the container alone. Yeah. So that's what Dalton's law says. The pressure of oxygen, pressure of any gas, any pure gas in a mixture is equal to the pressure if it occupied the container alone. That's all that Dalton's law states. Thank you for watching.